All right, welcome back to our next talk in the area of steel design. Today's lesson will be about beam bearing issues, okay, more specifically support reactions and how do we protect a beam when large concentrated forces are landing in a very small location, all right? Typically in our statics and structural analysis classes, we always assumed that, a support reaction on a beam was with some sort of concentrated load. So say like at the end of the simply supported beam, we always assumed that it was kind of a point load happening there. But in reality, okay, that load is actually spread out over some distance, okay? And the size of that distance matters, right? Because, if this plate gets really, really small, this load starts to look more like a point load, but and typically with very large values, especially at support reactions, 80, 90, 100 kips or more is not uncommon. A concentrated load like that sitting at a singular point on a beam has the potential to cause damage to the beam itself. Outside of the things that we've been designing, as far as shear goes or as flexure or whatever, okay? So we've got to make sure that we're able to get these forces from the beam transmitted into whatever support this is, whether it's the top of a concrete wall or into the top of another beam. We want to make sure that we don't have any problems in these localized effects, okay? And likewise, maybe this is the support from a from a cross member coming into the page, and it's the same issue. So we've got some things that we have to kind of look at on there. Okay, now there are a whole lot of these categories. We're going to focus our talk on two primary ones this time, okay? And both of them are found on the same page in the AIC code in the 15th edition. Okay, the web crippling will be one of them that we talk about, and then web yielding will be the other, okay? So this is J10.3 and J10.2, all on page 1-143 of the 15th edition. All right, now I'm tossing in concrete bearing because we use that for column base plates, okay? And we've talked about those in another video or in class, okay? And I wanted to provide you the link for that. That's on a couple pages earlier on J8. So this chapter J is actually about the design of connections, okay? And a lot of odds and end bits of information and requirements are located in chapter J. All right. Now the first one that we're going to talk about is web yielding, okay? And so we'll point out right off the bat that for web yielding, okay, we're used to seeing yielding phi being a 0.9, but for this criterion, phi is equal to 1.0. Okay, it's a very there's a lot of residual capacity in this. This is a very approximate method for estimating these values, okay? And you'll find that these values are very, very large. These capacities that cause problems, the numbers are going to be massive that we're going to deal with, okay? All right, now, there are two things that we have to kind of consider as we're looking at this, okay? We're going to define the width of the bearing plate at some dimension n, okay? So here, this is the width of the bearing plate out at the end of the beam, okay? And then n is also the width of the bearing plate of this guy in the middle. Now, they can be different. You do each of these calculations separately. But the idea is that if I have my point load reaction here, it wants to fan up into the beam and then eventually spreads out. And they typically assume this is like 45 degrees or some measured amount. And I'll show you how to calculate that here in a second. Okay. The things that you have to realize as you're looking at these bearing criteria is that they're going to split this into two categories. Okay. The first one is that we're looking at either an end region of a beam, because if you look at this, there's no way for that portion of the stress to develop, okay? And so it gets cut off by the end of the beam. It's one of the reasons that we like to have a little bit of extra length beyond the bearing pad is we actually get a little bit stronger surfaces, but sometimes it's not always the case. So we got to make sure that we're looking at that. All right, let me get that off of there. Okay, and then at the interior of the beam, you'll see that you can actually form this kind of trapezoidal stress region as in both sides of it. Okay, so this one I'm able to go from here, and I'm able to go from here, and so I get the general shape of it. Whereas at the end, it was only one side. So that's the first thing you have to keep in mind is this an exterior support or is this an interior support? Okay, and the way that it's classified is based off of the dimensions that we have. Okay, web yielding, okay, is assumed to be a criteria in which a point load transmits, through the bearing plate into the top flange of the beam, Okay, and then as all that load, if you look at the cross section of what we have here of an I-beam, imagine this bearing plate is the full width, of the entire section. All of this load is funneling into the web and then going down to the bottom so that it can now travel through the beam and come out the other side. Okay, so the critical spot on this is generally right either at the top of the fillet or at the bottom of the fillet, all right? And so in the AIC manuals, this is that K dimension, okay? And it's the dimension that goes from the top of the fillet to the top of the beam, or from the bottom of the beam to the top of the bottom fillet. Okay, those are the critical locations that we're worried about, because all this load is getting collected and we could overload. We have a big area here and a small area here. We're looking to collect all this load and transmit it through the beam into another part of the structure. So that's our critical location for for web yielding. Okay, all right. Now the process is very, very easy. Okay, the dimensions that we have to worry about are, as we talked about, that the width of the bearing plate, that's N, and this is generally the factor that you have some control over, okay? And then for the case of an exterior support reaction, I get an N width plus another 2.5 times that K value, okay? And that's assumed to be the critical location of this load as it starts to spread out a little bit, okay? In the interior region, this guy is interior, okay, and this one was exterior. Okay, the interior region, I get the N width again, and then I get 2.5K on one side plus 2.5K on the other, for a total of N plus 5K. Okay, now typically this is measured in inches. Make sure your N and your Ks are all the same units. That's no major deal. Okay, after that, all you do is it's basically a plug and chug type of calculation. Okay. So the nominal strength, or the maximum load this beam can take without failing in web yielding, is for our end regions, which is our exterior case, again, exterior, okay, and for our interior is this formula here, and it's very, very simple. It's basically the load, or the reaction value, is 5K plus N, okay, multiplied by the yield stress, multiplied by the web thickness. All right, so it's literally the stress that can be developed over that particular region. And so if you kind of look at, we had that trapezoidal region in the middle on this thing. If I look at this in 3 dimensions on here, what's happening is all that load is getting piled on to that region, and it's being resisted by whatever's happening on the bottom. All right, and so this dimension is my TW, all right, because that was the width of our beam up here at the location that we're worried at, our critical section. And then this dimension here is N plus 5K, okay, or N plus 2.5K for the ends, but for the interior it's N plus 5K. That's all there is to it. It's just basically a stress transfer calculation, all right, and so that would be our capacity that would cause yielding on that area. Okay, so it's very, very easy, very, very simple. Okay, for the exterior region, it's the same formula, except the only thing that changes now is that first term, okay? Instead of being 5K plus N, it's now 2.5K plus N. And again, that was coming from the dimensions of what we assume to be the stress block that could develop, or the critical region, if you will. Okay, so super, super easy for us to be able to do that. Okay, so the next criteria that we have is web crippling, okay? And because this is more of a stability issue, we're going to be required to have a resistance factor of 0.75, okay? Now, the phenomenon of web crippling is not so much a yield phenomenon, but more of an instability that develops in the web, whereby, because of the loads that are transferring through the beam, I actually experience a buckling of the web of the beam at a local location, all right? So there's a whole lot of plate bending theory that goes into these formulations as we look at it. But the basic premise is this is my I-beam cross-section, and I put a load or some sort of stress up on top, and I put a stress somewhere on this. We already discovered that all this load is trying to funnel into the web, okay? And so potentially what happens is, if I draw a node there and I draw a node there, this web, depending on how tall it is, could actually start to buckle out of the plane of this thing, okay? And that's what we call web crippling. We're basically reducing the strength of the beam because we're buckling the web at some localized location, particularly where the point loads are at. Okay. All right, so the formula is, well, it looks a little nasty. It's not bad. Okay, it's pretty straightforward, that for an internal load, so this is an interior region of the beam, so we're still being bound by that interior-exterior criteria that we had before. For an interior load on a beam, it's 0.8 times TW squared times 1 plus 3 times N over D times TW over TF, all raised to the 1.5 power. All right, so the N, again, is the width of the beam. If you remember on our graphic, N was the width of the bearing plate. Okay, and then everything else is pretty self-explanatory. D is the depth of our beam. Okay, TW is the width of the web, so that's kind of a measure of the strength of the web. And then of course TF is the thickness of the flange. Okay, and that's how we start to establish the formula. Now that whole quantity gets multiplied by this radical term, which again is E times Fy times TF over TW. So it's pretty much just a plug and chug calculation. Okay, now this one is a little bit different. So this is our interior load. Okay, now where by web yielding we were looking at the formation of these critical stress blocks, and if I could form this thing fully, it was interior, and if I got truncated on one end of it, it was considered as exterior. Okay, what happens with this is that they define an interior load, okay, as basically being a distance of d over 2 from the support. Okay, if you're more than d over 2 from the end of the support, okay, you are assumed to be at an interior location, you get the full strength. But the problem is that if I start getting out toward the end of this beam on here, and I'm within that region, okay, you're losing a lot of, if we come back, I keep coming back to this picture here, if you're in this region here, I'm losing a lot of strength by these lateral elements that are not here, that are missing. So, if this is my critical location for interior, I got some strength that's being provided by this part of the plate, and I get some from the other side that's all trying to stabilize this thing. It's a very complex mechanism, whereas at the interior or at the exterior region, okay, I don't have that region, okay, and so they're assuming that distance is d over 2, okay, whereby it's that's our problem region if you look at it. Okay, all right. Now, once you decide whether you're interior or exterior, it's a matter of plugging in the formula. Okay, so we've talked about the interior formula. It's not too bad. Okay, what we're looking at now then is looking at these ratios of the width of the bearing plate to the depth of the beam. Okay, and so if we're at N over D less than or equal to 2, I'm using this formula. Okay, so N over D less than 0.2. Okay, this means that it's a very narrow width on this compared to the depth. Okay, this value is basically half of the value that we had from the interior loads. Okay, but if I have a very wide plate, okay, in comparison to the depth, and again N over D greater than 0.2, the formula changes a little bit. All right, okay, so we're 0.4 times TW squared, and then this term inside the bracket starts to change, and then the radical at the end is very similar to what we had before. Okay, so the interior part of the bracket is 1 plus, then the quantity 4N over D minus 0.2, okay, and then all multiplied again by that ratio TW over TF raised to the 1.5 power. So the only piece that changes is this guy and that numeric quantity out there in the front. Okay, so that's all you have to kind of keep your eyes out for. So you check N over D less than or equal to 0.2, and then N over D greater than 0.2, and we're good to go. And again, for all of these, phi is 0.75. Okay. All right, so for our example, I just want to give you kind of a sense of the numbers, the size of the values that we're talking about here. For a W12 by 53 of A36, we're going to determine the nominal capacity for web yielding and web crippling for an interior region. So again, you're kind of looking for this of the beam. Oops, lost an M. Okay, if the bearing plate is 12 by 12, okay, so depending on how this plate is oriented, this could be an N by an N. All right, now kind of an interesting side note on this. A lot of times if we can make our bearing plates square, that helps with the fabrication, because then we don't have to worry about, well, what if they turn the plate the wrong direction? Is my N still in? Because remember, N is measured along the length of the beam, okay? It's not across or across the cross section on this thing. All right, so all we do is basically we run through the calculations, we go look up our data for a W12 by 53, the web thickness is 0.345 inches, the flange thickness is 0.575 inches, K is measured to be 1.18 inches, and then D is 12 inches on these. Okay, so for web yielding for this interior location, we're going to take the formula 5K plus N times Fy times Tw. And if I plug in all of those values and I shake it up, I get a load value of 224 kips. All right, so something like 112 tons will cause web yielding in this beam. So these are massive numbers on this. Okay, all right, running through the formula for web crippling really quick. Okay, now again, we're at an interior region, so we're using the first formula where we don't have to look at that N over D less than 0.2 ratio. Okay, so it's just 0.8 times TW squared times this quantity in the brackets that you saw earlier. Okay, multiplied by all of our radical stuff. There's E, there's Fy, here are our dimensions for the flange and the web. Okay, and if I do that, that capacity is 300 kips, so it's even more, okay, because these sections are very, very strong on those. All right, and I see that we have a typo there. Okay, that this should be 224 kips on that set of notes. Okay, all right. Now, the 179 number happened to actually be the value of it out at the exterior region, but I wanted to kind of get these things consistent so you could kind of start to see. Okay, all right. With that being said, that will end our discussion on web crippling and web yielding. Hope it makes sense. Okay, if you've got any questions, please leave a comment down below, and we will go from there. I'll see you guys next time. Thanks. Bye.